video we will explain about the working of a DRAM memory. So this is DRAM memory is dynamic random access memory, and here it is less expensive because each cell is made up of capacitor and transistor, and the number of transistors are less as compared to static RAM implementation. Then this is the circuit diagram corresponding to a single cell. Here we have one transistor and one capacitor, and the information is stored as a charge on the capacitor. So this transistor will be used as a switch or pass transistor, and the gate input is connected with the word line, and this is connected with the bit line also, this part. Then when the word line is activated, this transistor will become turned on, and the content will be the charge on the capacitor will reach into bit line if it is charged or it is discharges through the transistor. And if there is no charge, then the voltage at the bit line will be low, that indicates a 0. So if there is a charge on the capacitor, that indicates 1, and if there is no charge, that indicates 0. Then the number of transistors in this case is only one transistor as comparing with the static RAM. In the case of static RAM, you have to use 6 transistors. That is why static RAM is more expensive comparing to the DRAM. But problem with this DRAM memory is information is stored as a charge on the capacitor, and the capacitor has a problem that its charge will there will be some leakage current, small leakage current, and the charge on the capacitor may discharge. Over time, the charge on the capacitor may discharge. So we have to dynamically refresh the content of the capacitor. That is why the name dynamic RAM or dynamic random access memory. Next, we have to explain the write operation in the case of a DRAM memory cell. So in this case, first the word line is activated. So this transistor will become turned on, and there is a path through this line. Then appropriate voltage is applied to the bit line. What value we have to store? If we have to store a 1 value, then a high voltage will be applied through this bit line. That will reach into the capacitor, and capacitor will be charged to a high value. That means 1 is stored there. Similarly, if we are applying if we want to store a 0 value, then we are actually giving some low voltage here. Then the capacitor will discharge, or the charge on the capacitor will remove, and this will become a 0. That means this causes a known amount of charge to be stored onto the capacitor. Okay, that's about the write operation in the case of the DRAM memory cell. Okay, next we can explain how the read operation will work. So first the word line is activated. So this transistor will become turned on, and here there will be a path. So if the value then the charge on the capacitor will reach, or the capacitor will discharge, and the voltage will arrive at the bit line. The sense amplifiers at the end of the bit line will monitor or sense the voltage, and if the value is above some threshold value, then it will identify that okay, the value stored in this capacitor is a 1. But the problem is during that time the charge now is less because that capacitor is now discharged. So the sense amplifier will drive the bit line to a full voltage that represents a logic value 1. This voltage recharges the capacitor to full charge that corresponds to logic 1 value. Okay, there is a refreshing answer. Then okay, if the value stored was a 0, in that case the sense amplifier or the sense right circuit at the end of the bit line will identify that okay, the value stored is a 0 value. Then it will pulse the bit line to a ground voltage or ground level. That will which ensures that the capacitor will have no charge representing a logic value 0. In this case also there is a refreshing is done. All cells in a selected row are read at the same time, which refreshes the contents of the entire row. Okay. Next you have to consider the or explain the 16 megabit DRAM chip configured as 2M into 8. So here the cell array is organized as 40 or 4K into 4K matrix. Then why we are arranging like this? Means in the case of a chip development, the number of word lines and number of bit lines must be equal or nearly equal, because that will improve the performance during the manufacturing of the chip or the okay. Then so we have arranged this cell array as 4096 into 4096. Then we have to configure this as 2M into 2 mega into 8. So the output bus with this is our output bus with D0 to D7. That is 8 bit wide. So the output will be available as 8 bit. Or during write operation, the input or the data bus with this, or we can call data bus with this 8 bits. So during read operation, output will be available through this one, and during write operation, data to be written is given through this bus. So this is actually indicates the width of the data bus. Then this cell array is connected with a row decoder and a column decoder. Then sense write circuits. Then this row decoder, as you know, this is used to select a row from the 4096 word lines, or to select a word line, or to activate a word line, or to select a row from 4096 rows. We have 4096 rows. So that will read an entire row, and we will have a row of length 4096 bit line. We will receive the content of 40. We will have the row value through 4096 bit lines. That is, assume that these are our 4096 bit lines. Then we already said that in this case our data bus width is 8 bits. So in this case, what we will do is we will group this into 8 bits. And again 8 bits like that. So how many such groups? 8 bit group. Because our data bus width is 8 bits. So how many such 8 bit group we will have? That is, we will have 512 such 8 bit, because we have 4096 bit lines. Okay. So in this case, we need only to select one of such 8 bit group from this sense write circuits, because each of these bit lines will be connected with a sense write circuit. So we need to select one such 8 bit group from the 512 groups. So for that purpose, how many bits will be required here? So for selecting such a group, we need this column decoder. So here we have a column decoder that is used to select a group from this group. In our example, 512 groups. So we need a column address. So in our example, how many bits required to select from 512 such groups? So we have 9 bits. 9 bits, that is 2 to the power 9 is equal to 5. So 9 bits are required to select a group from this bit length or from 4096 bits. Okay. Then here this is raw decoder. In case of a raw decoder, we have to select one row or one word line from 4096 word lines. Then how many bits are required? We require 2 to the power 10 is equal to 1k, 2 to the power 4 is equal to 2 to the power 2 is equal to 4. So this is actually 4k. So we need 12 bits. 12 bit address is required to select one word. So total number of address bits required is equal to 12 plus 9 is equal to 21 bits. 21 bits address are required to select one byte here, one byte of information from our 2m into 8 or 16 megabit DRAM memory. Okay. So we have an address 21 bit address. Total 21 bit address is required for selecting for reading or writing one byte of information in this example. In this example, 1 byte, because our data bus width is 8 bits for 1 byte. If we are using 16-bit data bus, then correspondingly we have to group into 16-bit groups. Okay. Then that's about the raw decoder and a column decoder. Then to reduce the number of pins, so here we need 21 address pins for transferring the address information. So to reduce the number of pins on the chip, we can use another mechanism. We can use a single 12-bit bus, and that can be used for transferring both the column address and a raw address. We can call this as raw address and this is column address. Okay. We can use a single 12-bit bus. Which one is maximum? Here 12-bit is maximum. So this 12-bit bus can be used for exchanging, for giving both, for transferring both the raw address and a column address. For that purpose, we have to use some other mechanism also. We will use some multiplexing mechanism. Okay. So for that purpose, we will use another unit, raw address latch. Raw address latch and a column address latch. Column address latch. So here this is our 12-bit bus. Then this 12-bit bus is connected with this one and this one. Here we assume that the bits 22A9. These are used as row address. Row address A8 to A0 column address. Like that. A22A9, which are used as column address, row address, and A0 to A8. These are used as column address. So we have a 12-bit bus, and this bus is used for transferring both the column address and the row address. We will say that is multiplexing. We are using a term multiplex. So what we will do is, this is connected with A22, A9 and A8 to A0. So at a time, one address will be transferred, either column address or row address. So first we assume that we are transferring the row address first, that is A20 through A9. Then that will be latched into this one by using a control signal RAS bar. This is actually row address stop. This is a control signal that will latch this information on this bus into this latch. So after some time, or after a few time, this address will be transferred through that is the column address will be transferred. Then the column address will be transferred through this bus. That will reach both to the latches, but here there is another control signal, that is column address stop or CAS. Column address stop. Okay, column address stop. That is actuated, so the column address will be latched into column address latch. For transferring both the row address, column address, we will use the same bus. That is why we are calling multiplexing. First row address is sent, that will be stopped by the row address stop control signal into the row address latch, and then column address is transferred. That will be captured into this column address latch by using this control signal CAS or column address stop. So now the row address is available here and the column address is available here, and we can perform the read operation. So the read data will be available through this data bus. So if you are performing a write, then that will be reached into here. Okay. Okay, next we can consider the read and write operation in the case of our memory. So, first we will apply the row address through our multiplexed bus. So that address will reach both this latch, but we will activate the row address stop. So, this row address will be captured into the row address latch, and the value present in the row address latch will be decoded by the row decoder, and the corresponding row will be selected from this cell array. Then all the that value will be available to the sense write circuit, and the sense write circuit will perform the read and refresh operation. All the cells on the selected row are read and refreshed. Then shortly after, the column address is applied to this multiplexed bus. Then the column address stop is activated. So the column address will be latched into or captured into the column address latch. The information in the column address latch is decoded, and the appropriate group of 8 sense write circuits are selected. That is what will be the value that will be decoded by the column decoder. Then based on the content, the corresponding group of bit lines will be, or group of sense write circuits will be selected. Okay. Then for a read operation, the output values of the selected circuits are transferred to the data lines D0 through D7. And for a write operation, the information on the data lines D0 through D7 is transferred to the selected circuits. This information is then used to overwrite the contents of the selected cells in the corresponding 8 columns. Okay, that's about the read and write operation in the case of a DRAM memory chip. Okay, we already explained that the information is stored as charge on the capacitor. So there is a chance of leakage current, and the charge may leak from the capacitor. So we have to dynamically refresh the content of each row. So to perform this refresh operation, there must be a refresh circuit. The refresh circuit will select each of these row and then refresh the content of that row. Okay. Next we have to explain the fast page mode operation in the case of a DRAM memory chip. When the DRAM is accessed, the contents of all 4096 cells in the selected row are sensed, but only 8 bits are placed on the data lines D7 through D0. A simple modification can make it possible to access the other bytes in the same row without having to reselect the row. A latch can be added at the output of the sense amplifier in each column. The application of a row address will load the latches corresponding to all bits in the selected row. Then it is only necessary to apply different column addresses to place the different bytes on the data lines. By applying a consecutive sequence of column addresses under the control of successive cache signals, bytes can be transferred in a sequential order. This allows transferring a block of data at a much faster rate. This block transfer capability is referred to as the fast page mode feature. Okay.